Welcome to Science Listener. Tonight you're not just looking at a comet, you're witnessing a messenger from another star. Its name is 3I/Atlas, and unlike any comet we have ever known, it does not belong to our solar system at all. It drifts in from interstellar space, carrying secrets of a world far beyond our sun. Right now, through the eyes of Hubble and Webb, it appears as a faint blur wrapped in a strange green glow. Some scientists whisper it could be nothing more than an exotic comet. Others wonder, is it the shattered core of a planet that never formed, or the frozen seed of one yet to be? It feels distant, but the encounter is already here. Atlas races past us at tens of kilometers each second. To our eyes it is just another point in the dark, yet on the scale of stars it is a visitor from unimaginable distance, a rare guest we may never see again. And questions rise. Is it a natural wanderer, or could it be something else? A fragment of creation, or even a fragment of technology? Before we dive deeper, tap like and subscribe. But only if you're curious how the universe itself can send strangers into our sky. And leave me a comment. Where are you listening from, and what does your night sky look like? In New York, city lights hide the stars. In Chile, the desert reveals the Milky Way in full. In Tokyo, someone drifts to sleep under the same glow that now hides 3I/Atlas. For centuries we imagine comets as eternal wanderers, omens or icy relics. But astronomy shows us they are more than frozen rocks. They are clues, fragments of birth, pieces of other systems torn away and sent across the void. And in Atlas we see a mystery, massive, luminous, defying easy explanation. Close your eyes and picture this. A dark traveller from another sun carrying the memory of a world we will never know, passing once, and only once, through our skies. In that silence you realise, the universe is not calm or still. It is alive, restless, and filled with strangers. This is where the story of 3I/Atlas begins. And beginnings are never loud. They come as whispers, as faint traces in the dark, something you almost overlook until the silence itself demands your attention. So why could 3I/Atlas be more than just a comet? Comets in our solar system are fragile. They break, they shed dust, they shiver under sunlight. They are short-lived spectacles, known for tales that flare and vanish. You've seen those images in books or news, glowing arcs across the sky, but everyone knows they are temporary. Their orbits wobble because jets of vapor push them. Their bodies fracture after too many passes near the sun. But Atlas does not bend to that script. It refuses the weakness. Its orbit has been measured more than 4,000 times across the summer of 2025, and it remains unshaken. The line it follows is clean, unperturbed by the gas it releases. That is not what fragile comets do. You track the numbers, and they point to weight. Tens of billions of tons, a nucleus more than 5 kilometers across. Oumuamua in 2017 was barely 200 meters, a sliver of a rock compared to this giant. Borisov in 2019 stretched perhaps a kilometer. Atlas is larger by orders of magnitude. When you stand under the sky and think of it, you feel that weight pressing into your chest. A traveller that carries itself like a world, not like dust. Where comets twitch under every breath of sunlight, Atlas drifts steady, unmoved. The chemistry deepens the divide. Ordinary comets are rich in water. They form in the icy regions of a system, with carbon dioxide as a minor trace. But Atlas brings a ratio flipped upside down, 8 molecules of CO2 for every one of water. That alone tells you it was born in conditions different from our Kuiper belt or Oort cloud. And then the glow. In September, during a lunar eclipse, telescopes caught its coma shining green. On Earth, you're used to that colour being caused by diatomic carbon, C2 molecules flaring under solar radiation. But Atlas betrayed no strong trace of those molecules. The light was real, the chemistry absent. You read the spectrum and it is like hearing a voice in the wrong language. The sound comes clear, but the meaning is foreign. When you look again at the images from late August, the Gemini South telescope shows a tail, thin, faint, stretched behind the body. But still the orbit does not change. You wait for the wobble, it never comes. If the jets are strong enough to make a tail, they should be strong enough to nudge the path. If the jets are too weak, the tail should be invisible. Either way, the paradox holds. This is not the behaviour of a fragile snowball. This is the behaviour of something denser, harder, older. Think of comets as crumbs, leftovers of formation, scattered and brittle. Then look at Atlas, a body that resists, too heavy to be pushed, too strange to be typed as ordinary, too persistent to be dismissed as dust. You stand there and ask yourself, if this is not a comet in the usual sense, then what is it? Every measurement drags the answer further away from fragility and closer to resilience. Its mass suggests solidity. Its chemistry suggests an origin in a place we do not know. Its stability suggests something more like the core of a planet than the edge of one. So why could 3I/Atlas be more than just a comet? Because it carries itself with gravity, not fragility. Because it glows with colours whose cause we cannot name. Because it moves with a steadiness that refuses the expected shiver. You look at it and you do not see a crumb, you see a survivor. And if it is not a comet, then the sharper question remains. What are you looking at? A planetary embryo, the frozen core of a world that never lived, drifting through our sky. Explanations never arrive as thunder. They take shape slowly, piece by piece, until the outline is too clear to ignore. A planetary embryo is not a poetic phrase. In the language of planetary science, it means a body large enough to dominate its surroundings, yet still incomplete. Dust, stones, and planetesimals collide over millions of years. Some fragments grow faster than others, feeding on their neighbours until they reach sizes from a few kilometres to a few thousand. These embryos are the seeds of planets, cores dense enough to attract, massive enough to resist, but not yet finished. When you think of Earth, remember that it too began as one of these bodies, assembled from dozens of collisions. You raise your head at night and realise that Atlas may carry the same identity. Its size and weight do not belong to the fragile category of comets. Tens of billions of tons of matter do not drift like powder. The orbit holds steady not because it is lucky, but because the body is too massive to be pushed aside. You're not watching dust vanish into sunlight. You're staring at something closer to the hardened beginnings of a planet. The chemistry strengthens the idea. Water should dominate a comet's breath, but in Atlas carbon dioxide overwhelms it. 8 parts CO2 for 1 part H2O, a balance foreign to our system. Such a ratio suggests birth near a star hotter than ours, where water ice could not survive, or in a disk where the elements were mixed differently. You follow that thread, and the air feels colder. Above you drifts not a child of our sun, but the orphan of another. Its glow confirms the strangeness. Green light spreads around the nucleus, but the usual molecule, C2, is barely present. The light speaks, but in the wrong language. You wait for the spectrum to explain itself, and it does not. Embryos are not peaceful. They carry violence in their history. Our own moon bears the memory. 4.5 billion years ago, a Mars-sized embryo called Theia struck the proto-Earth. The impact melted crust and mantle, and from the debris the moon was born. That collision was not unique. The early solar system swarmed with such events. Embryos merged, shattered, scattered. You picture Atlas as one of them, but in another star's domain, circling a young sun, colliding, competing, until one encounter tore it loose. Cast outward by gravity, it carried its unfinished identity into the void. You stand beneath today's sky and feel the distance. The object above you could have been a planet if chance had played differently. The mass, the chemistry, the glow, the resilience, all align with the thought that Atlas is not simply a cometary leftover, but the remnant of planet-making. You know comets as temporary, fragile, quick to vanish. Atlas is stubborn. It resists the sun. It carries the weight of a world in miniature. You stare, and the question is no longer whether it is a comet. The question becomes what kind of world it almost was. Planetary embryos do not always succeed. Most never become planets. They collide and are absorbed, or they are exiled into interstellar night. Earth was lucky, others were not. Atlas could be one of those exiles, a survivor that never grew, never fused, never found a place to settle. You let the idea sink in. Over your head drifts a frozen possibility, a body that carries the memory of a system now gone. So when you call Atlas a planetary embryo, you are not inventing a fantasy. You are recognizing the seed of a planet that never bloomed. The fossil of creation, still intact. A reminder that worlds are fragile in their beginnings, and most never survive. Yet this embryo did not vanish. It left its home. It crossed the gulf. It arrived here. Which means the next part of the story is exile. How such a body is torn from its system and condemned to wander. Exile in space is never quiet. It begins with gravity pulling in one direction, then another, until a body is caught in the crossfire and flung outward into darkness. In the early years of any star system, orbits are not serene. Embryos circle their sun while giants rise from the disk, massive planets forming quickly and reshaping everything around them. Gas giants in particular act like predators. Their gravity bends paths, destabilizes neighbors, drives collisions. Some embryos merge to grow larger, others are broken into fragments. The unlucky ones approach too close to a giant, are gripped by its pull, and are hurled away on escape trajectories. That is how exile begins. One gravitational encounter too many, one orbit turned from closed to open. You picture Atlas in such a scene. A young star overhead, a disk of dust and ice crowded with dozens of bodies, collisions shaking the skies. In the chaos, a giant stirs, maybe a Jupiter-like world, maybe something even larger. The embryo that would one day become Atlas strays too close, its orbit twists, momentum builds, and in a single pass it is thrown outward. Not destroyed, not shattered, simply rejected. You stand beneath tonight's sky and feel that violence across light years. The object you see was once caught in the grip of a giant and flung into the void. Astronomers model this process and see how common it must be. Simulations of planetary formation suggest that countless embryos are lost this way. Our own solar system is thought to have ejected more than it kept. Jupiter and Saturn, with their immense gravity, acted like slingshots, expelling bodies that might otherwise have become planets. For every world that survived here, perhaps dozens were cast into exile. Atlas could be one of those orphans from another star, proof that systems bleed matter into interstellar night. You follow its path now and realize how long it has wandered. Millions of years, maybe billions. Each step of the orbit stretches into emptiness. No return, no anchor. Radiation has battered it. Cosmic rays have scarred it. Yet it still holds together. That endurance tells you something. Only a dense, massive body could have survived such a journey. Fragile comets dissolve in the void. Their ice is stripped. Atlas persists. You lift your eyes and feel the scale. The object above you is a refugee that has crossed gulfs too vast for imagination. Exile also changes identity. Once it was a competitor in a planetary nursery, locked in battles with siblings. Now it is a wanderer, unclaimed, carrying only inertia. You know the difference because Earth itself could have shared that fate. Had a collision gone differently, had Jupiter pulled with greater force, the world beneath your feet could have been cast out. When you realize that, the sky feels heavier. Atlas is not only a visitor, it is a mirror of what might have happened to us. The exile of Atlas matters because it is not unique. If this one reached us, there are others. The interstellar medium is not empty but filled with seeds, fragments, embryos lost in gravitational wars. You think of how many drift unseen, passing between stars in silence. Atlas is simply the one we caught in our field of view, the one whose path brushed near enough for telescopes to notice. For every one we see, perhaps millions remain invisible. So exile explains why Atlas is here. A world seed cast out by its home, wandering for ages, carrying strange chemistry and alien weight. You look at it and understand. It is not only a comet, not only an embryo, but also a refugee. And refugees do not travel empty-handed. They carry the potential to plant new life where they go. That thought opens the next question. Can bodies like Atlas seed planets, or even the conditions for life in the systems they pass? Stories of creation are never tidy. They spread like dust across the wind, carried from one place to another until something takes root. When you think of Atlas as a seed, the idea is not metaphor but physics. Interstellar bodies carry matter, frozen molecules, fragments of chemistry born in other suns. Every time such a body passes through a star system, it brings with it ingredients that may not exist there. You stand under the night and realize, if one object like this has reached us, then billions must wander, crossing the galaxy like silent messengers. Most go unnoticed, but each one carries the potential to change the places it visits. You follow the chemistry first. Atlas exhales carbon dioxide in unusual proportion, water in rare trace, cyanide radicals glowing faint in spectra. These are not just numbers, they are pieces of a recipe. You breathe air on Earth shaped by oxygen released by life, but before life, chemistry had to be delivered. Scientists argue that comets and asteroids in our own system brought the volatiles that became oceans and atmospheres. Now imagine an interstellar visitor doing the same. You feel the scale. Every crossing body could deposit molecules, dust, even micrograins of organics into alien disks. Some fraction of life's building blocks may not be native but carried across gulfs. The weight of Atlas also matters. Smaller comets disintegrate quickly, leaving little more than dust. A body this massive can endure heating, survive long passages, scatter material along the way. Each fragment shed becomes another seed. You picture a disk around a young star, thick with gas and stone, and then an outsider arrives. Atlas cuts through, leaving traces in its wake. A streak of alien chemistry mingled with native matter. Later, when embryos there accrete, they inherit those additions. You stand beneath your own sky and wonder, how many worlds carry genes of strangers from beyond? history gives clues. Earth itself may have received water from icy bodies migrating inward. Carbon compounds too may have rained down from comets. If this process shaped our world, why not others? You tilt your head back and the thought sharpens. Maybe Atlas has already seeded places before. Maybe its trail has brushed other stars, leaving behind particles too small to notice, yet large enough to matter. A refugee can also be a sour. The green glow becomes symbolic, not just chemistry but a sign. The body breathes something alien. You watch it and realize you're looking at the potential for worlds elsewhere. In silence, Atlas offers a reminder that creation is not contained in one system. The galaxy is a network of exchanges, fragments passing from star to star. You feel the weight of that thought. The sky above you is not closed. It is porous, alive with crossings. So Atlas can be more than a comet, more than an embryo, more than a refugee. It can also be a messenger, a carrier of seeds, not biological in the sense you know, but chemical, foundational. Worlds are built by what they inherit, and Atlas may be part of that inheritance. You ask yourself, if a single fragment of alien chemistry changes the balance in a young disk, does it alter the story of that system forever? You breathe out under the stars and the answer feels close. Exile does not mean emptiness. Exile can mean transport. A body lost by one star may become the fertilizer of another, and Atlas, crossing now, shows you that the galaxy is not a set of isolated gardens, but one vast field where seeds drift endlessly. Which brings the story back to us. If such bodies can seed others, then our own system too has been seeded, and may seed in turn. Atlas is proof of exchange, a sign that matter travels, that stories of creation are shared. The next question presses close. What does this mean for the future of our sky, and for the heritage of the world still forming? Speculation often begins where data falls silent, and the silence around Atlas has already invited voices bolder than most. The most striking of those voices belongs to Avi Loeb, a Harvard astronomer known for pushing against consensus. In September 2025, he suggested that Atlas might not simply reflect sunlight. According to him, the brightness of the coma could be evidence that the object is producing its own light. To call a comet luminous is to break the rules of what comets are. They shine by scattering sunlight from dust and ice. If Atlas shines by itself, the category collapses. You read the reports and the claim is clear. Images taken in August and September show a glow inconsistent with the expected amount of dust. The nucleus is estimated to be massive, heavy enough that weak outgassing should not produce the brightness recorded. If the dust is too little, then where does the light come from? Loeb's answer is unsettling. Perhaps Atlas carries an internal source, maybe radioactive decay, maybe engineered power. You stand under the night sky and feel how that suggestion changes the way you look up. A faint blur is no longer passive. It could be active, alive in some way, even if only as a machine. This is not the first time Loeb has spoken this way. In 2018, he argued that Oumuamua, the first interstellar visitor, might have been artificial, a light sail pushed by starlight. That claim drew criticism but also attention. Now he applies the same lens to Atlas, an interstellar body whose mass and brightness do not match easy equations. You follow the debate and the rhythm feels familiar. Scientists weigh dust, gas, reflection. Loeb insists on anomaly. The public hears the word alien and leans closer. The power of the idea lies not in proof but in contrast. Natural explanations stumble because the chemistry does not fully explain the glow. artificial explanations do not need much detail, only the suggestion that the light is deliberate. You tilt your head and the thought sits heavy. If a comet is glowing by itself, the universe feels closer to us, less indifferent. Whether Loeb is right or not, the claim forces a shift. Atlas is no longer only a frozen embryo, a refugee, a seed. It is also a candidate for artifact. That possibility alone guarantees attention. Arguments in favour of such a claim grow from numbers that refuse to behave, from brightness too strong and motion too steady to fit the label of a comet. The first piece of support is the brightness itself. In late August and September 2025, telescopes recorded a coma shining more strongly than expected. The dust surrounding Atlas appeared too thin to scatter that much sunlight. Calculations of particle density and grain size did not add up. If the coma was faint in mass, then why was the glow so intense? You stare at the data and feel the mismatch. The object is brighter than it has the right to be. The second argument lies in stability. Comets normally show slight deviations from pure gravitational orbits. Jets of gas shift them, sometimes by measurable amounts. More than 4,000 positional records for Atlas showed no such drift. The orbit was hyperbolic, clean, untouched by any push. You follow the curve across the charts and see a body that behaves as if engines of chance do not apply. A natural comet this heavy is rare. An engineered object that resists deviation fits just as well into the numbers. The third piece is scale. Oumuamua was a sliver, Borisov a small comet. Atlas is larger by far, a nucleus estimated at more than 5 kilometers across. That scale brings with it a paradox. Too massive for outgassing to move, yet too bright for dust alone. The combination of heft and light leads those sympathetic to Loeb to ask, what if the glow is not reflected at all? What if it is emitted? You tilt your head upward, and the question lingers heavier than the sky itself. The fourth element comes from comparison. Oumuamua accelerated in a way not explained by gravity alone, prompting speculation of propulsion. Borisov behaved more like a normal comet, but still carried exotic chemistry. Atlas now blends both, an orbit too perfect, chemistry too odd, and a glow that defies. You stand beneath the night, and the pattern feels deliberate, each interstellar visitor stranger than the last, each one feeding suspicion that randomness is not the only force at play. Together these arguments form a chain. Unusual brightness, immense mass, orbital purity, and strange chemistry. None alone prove anything, but taken together they leave space for doubt. You breathe in the cool night and understand why the idea of an artificial source refuses to die. Atlas behaves too much like something designed to be noticed, too little like a comet content to crumble. Still, for every argument in favour, there are counterpoints waiting. Natural explanations persist, and many astronomers insist that the anomalies can be solved without invoking machines. To weigh the balance, the next step is to examine those objections. Doubt grows strongest when imagination runs ahead of evidence, and the evidence for Atlas still allows paths that lead back to nature. The first objection points to dust itself. Comets are messy, irregular bodies. Brightness is not always proportional to the amount of visible material. Dust grains can be unusually reflective, scattering more sunlight than expected. If Atlas carries fine, silicate-rich particles, the coma could appear bright without needing extra sources of light. You look at the numbers again and feel how easily reflections can deceive. A glow does not have to mean a lamp. Sometimes it's just a surface that catches the sun too well. The second objection rests on mass. Yes, Atlas is heavy, but that explains the lack of non-gravitational drift. A nucleus this large cannot be nudged by weak outgassing. The clean orbit does not prove propulsion or design, it simply matches inertia. You follow the orbital data across the charts and realise what some call anomaly, others call stability. The third argument against the artificial view is chemistry. Strange ratios of CO2 to H2O do not require technology. They require only a different nursery. Protoplanetary disks vary. Stars burn hotter or cooler, their radiation reshaping the balance of ice and gas. Atlas may be exotic to us because it was born under rules we do not share. You tilt your head back under the night sky and accept how vast the range of possible cradles really is. The fourth objection focuses on history. Oumuamua's acceleration caused uproar, yet later studies suggested that outgassing of unseen ices could explain it. Borisov looked strange, but still fit the pattern of a natural comet. Why should Atlas be different? The pattern holds. Each new interstellar visitor feels unusual only because our sample size is so small. 3 objects do not define a standard. You stand in that thought and feel the humility it demands. Strangeness is not proof of intent. A final counter-argument comes from skepticism itself. Extraordinary claims require extraordinary evidence. Artificial light would be extraordinary, and so far Atlas offers only unresolved data. No radio signals, no patterns, no structures, only numbers that feel awkward. The leap to design may be less science and more desire. You breathe the cool night air and admit, anomalies are attractive, but nature is full of them. So the debate turns into a balance. Brightness explained by dust, orbit explained by mass, chemistry explained by birthplace, history explained by sample size. Each objection pulls Atlas back toward the realm of natural bodies. Yet even as you follow them, the allure of the other path remains. Which raises the final question: why does the idea of an artifact, however unlikely, continue to hold our attention? Fascination grows not only from data, but from the way unusual numbers touch imagination, fear, and the hunger for meaning that silence alone cannot satisfy. For centuries, comets have been mirrors for human worries. In the year 1347, when the Black Death spread across Europe, chronicles linked the plague to a blazing light in the sky and wrote that deadly vapours had fallen from cometary tails. During the Great Famine of 1315 to 1317, hunger was blamed on heavenly omens, as if bright streaks across the sky poisoned the fields themselves. In 1910, when Halley's Comet returned, newspapers printed warnings about cyanogen gas in its tail. Shops even sold anti-comet pills. Bottles of sugar tablets promised as protection from a cosmic poison that never came. Every age projects its own fears upward, turning a faint blur into a sign of punishment or salvation. The 21st century is no different, only the language has changed. Where medieval Europe saw divine wrath, a world of satellites and machines sees technology. When an interstellar body like Atlas appears brighter and heavier than expected, the leap is easy. Perhaps the light is not reflection but intention. You read the reports, and the feeling is obvious. Numbers alone do not spread this quickly, but the word alien does. You sit with that thought and feel the pull it exerts. The universe is mostly silent, and silence is difficult to bear. The idea of a machine drifting across our sky feels like a break in that silence. Even without evidence, the suggestion carries a strange comfort, as if the cosmos itself had finally looked back. The ratios of CO2 to H2O, the absence of orbital drift, the calculations of mass, they stay locked inside academic papers. The suggestion of contact escapes those boundaries instantly. Media turn speculation into spectacle. A scientist makes a comment, a journalist amplifies it, a headline carries the word alien, and within hours the possibility travels further than any dataset. The public does not linger on charts of spectral lines or the precision of astrometric records. Attention flows to the question of intent. Could something from beyond have been built, and is it crossing here now? The fascination is not proof, yet fascination itself has power. It pulls eyes to telescopes, fills conversation, and forces even skeptics to answer. Skeptics continue to remind that the evidence does not demand this leap. Brightness can be explained by reflective dust. Orbits can be explained by mass. Chemistry can be explained by different nurseries. Yet they admit, reluctantly, that the idea of artificiality has a hold stronger than ratios and probabilities. The body is bright, massive, strange, qualities enough to make it compelling. Add the shadow of design, and the effect multiplies. You tilt your head to the sky, and the thought lingers longer than numbers, not because evidence confirms it, but because the idea itself fills the silence of space with intention. It transforms a cold object into a possible message. Even if reason pulls you back toward dust and ice, the trace of that other possibility remains, waiting behind every measurement. The fascination endures because it asks a question larger than data can settle. Are we truly alone? Or do the things crossing our sky sometimes carry more than mass and chemistry? Atlas remains unusual, and as long as anomalies resist easy answers, the possibility of intention will accompany every observation. Measurements will continue, spectra will be logged, orbits refined. Yet the suggestion of something more deliberate will not leave. The thought presses further, toward the future. Atlas is bright today, but its path is still unfolding. The next observations will track not only its coma and tail, but the exact way it moves through space. The fascination of design will linger, but attention must return to what can be measured: its orbit, its chemistry, its behavior under the sun. Movement tells more than light, and the movement of Atlas has already revealed something most comets cannot hide. When astronomers speak of non-gravitational accelerations, they mean the tiny nudges that comets receive from their own outgassing. As sunlight warms a nucleus, gas jets push against the body, altering its orbit by small but measurable amounts. Even fragile comets only a few kilometers across betray this behavior. Their paths shift slightly away from pure Newtonian prediction. The data is usually clear within months of observation. Atlas does not play by that rule. Across more than 4,000 observations taken between May and September 2025, its motion has followed a perfect hyperbolic arc, the clean line of gravity alone. No deviations, no measurable pushes from jets, nothing that betrays weakness. You study the orbital charts and realize that Atlas drifts like a stone too heavy for breath to move. Where others twitch, this body holds steady. The absence of non-gravitational acceleration is not a minor note. It is a defining feature. It means that either the body is unusually inactive, refusing to shed enough gas to be noticed, or it is so massive that the gas it releases cannot matter. Both conclusions push Atlas away from the comet label. You lift your eyes at night and feel the difference. The point of light above you is not trembling under the sun's touch, it is indifferent. This behavior sets Atlas apart from the earlier interstellar visitors. Oumuamua showed unexplained acceleration, one reason why Avi Loeb suggested artificial propulsion. Borisov released gas like a normal comet. Its orbit perturbed in the expected way. Atlas does neither. it remains massive, calm, immune to pressure. You breathe in the night air and the thought fixes itself. A body from another star is crossing our system without yielding a fraction of control to sunlight. The conclusion is unavoidable. The orbit says wait. Tens of billions of tons must anchor the trajectory so firmly that nothing shakes it. To understand how much weight that is, the next step is to measure the scale directly. The size of the nucleus itself. Movement tells more than light, and the movement of Atlas has already revealed something most comets cannot hide. When astronomers analyze comets, they expect to find small irregularities in their motion. Sunlight warms their surfaces, ices sublimate, gas escapes in jets, and those jets act like thrusters. The effect is weak but persistent. It shifts orbits, sometimes by a few kilometers over a season, sometimes by more. In the case of Halley's Comet, for example, such accelerations had to be included in calculations to explain its predicted return. Without them, the orbit never matched the sky. This is standard. It is part of how fragile icy bodies behave near stars. They cannot hide their weakness. Atlas should behave the same. It is a body that glows, that shows a coma, that carries a faint tail. All signs point to activity, and activity means gas jets, and jets mean orbital shifts. Yet in the summer of 2025, more than 4,000 individual observations taken from ground-based telescopes showed no sign of non-gravitational acceleration. Each measurement fell exactly where gravity alone placed it. The arc across the sky matched a hyperbolic trajectory with astonishing precision. No measurable deviations, no wobbles, a perfect curve. You look at those charts and the impression is stark. Ordinary comets tremble under sunlight, their orbits bending in small but detectable ways. Atlas moves like a stone hurled across space, too heavy to be pushed. It ignores the sun's breath. You stand beneath the same sky, knowing the star that dictates the fate of planets and controls the flow of comets cannot move this visitor by even the width of a hair. The absence of non-gravitational accelerations leaves two options. Either Atlas is strangely inert, releasing so little gas that its activity is almost negligible, or it is so massive that the gas it does release cannot matter. Both possibilities make it different. A dormant comet could stay invisible, but Atlas is not invisible. It shines with a green halo, its chemistry active. That makes the second explanation more likely. The body is massive enough that sublimation does not push it. This conclusion shifts Atlas into a category beyond fragile comet nuclei. The contrast becomes sharper when placed beside its predecessors. Oumuamua, the first interstellar object observed in 2017, showed acceleration that gravity could not explain. This became the spark for Avi Loeb's suggestion that it might be artificial. Borisov, discovered in 2019, behaved like a more familiar comet, showing gas release and the orbital deviations expected from it. Atlas joins this lineage differently. Its orbit shows no deviations at all. The Sun has no leverage. In this way, Atlas is both more ordinary and more extraordinary. It behaves like a massive rock, immune to outgassing, yet carries the visual signs of activity that should betray weakness. This stability is not a curiosity, it is a defining clue. The dynamics of its path require a mass immense compared to other comets. Tens of billions of tons are needed to explain why the jets fail to matter. The object follows gravity alone because its inertia is overwhelming. You follow the reasoning step by step and the picture becomes unavoidable. A nucleus on the scale of kilometers across, compact and dense, built not like a crumb but like a core. You breathe the night air and the fact sinks deeper. Atlas is not being moved. It travels through our system untouched, on a path determined only by the gravity of sun and planets. That means the forces that shape comets do not shape it. It is indifferent. The significance of this indifference is clear. This visitor is not fragile ice. It is something larger, stronger, more resistant. The absence of non-gravitational acceleration tells us what comes next. If sunlight cannot push it, then the only explanation lies in its weight. The next step is to estimate that weight, to measure the invisible anchor that keeps Atlas steady while other comets shake. That is where the story of mass begins. Weight in space is not felt by the hand but seen in the orbit, and Atlas carries more of it than any interstellar visitor measured before. To understand how much weight Atlas holds, astronomers rely on precision. The trajectory alone gives the clue. A body drifting through the solar system that shows no sign of gas-driven drift must be carrying enormous inertia. From the stability of the orbit, estimates place the mass of Atlas in the range of tens of billions of tons. This number is not abstract. It means a single body outweighs the entire fleet of ordinary comets discovered each year. Most comets are featherweights, fragile lumps of ice and dust. Atlas is closer to a planetary fragment, a survivor with gravity strong enough to dominate its own emissions. You stand beneath the sky and think what those numbers imply. 1 billion tons is already beyond comprehension, but Atlas carries not 1, not 10, but dozens of billions. It is a figure that demands comparison. Mount Everest weighs less than this visitor. The Great Pyramid of Giza could be built 100 million times and still fall short. The mass of this one body rivals the combined weight of every structure humanity has ever raised. You lift your head, and the blur above is no longer just faint light. It is a giant. Mass does not only resist sunlight, it defines survival. A body of this scale can endure what smaller comets cannot. Radiation, cosmic rays, collisions with dust grains in interstellar space. All the hazards that erode fragile comets over millions of years leave little mark on something so massive. The fact that Atlas arrived here intact tells its own story. To cross for millions or billions of years and still shine means its nucleus was never small. Weak comets dissolve long before such a journey ends. Only something with real weight can make it this far. The consequence is simple. Atlas is not a fleeting wanderer. It is a body that will pass through and continue, losing little of itself in the process. Even as it grows a faint tail, even as gases vent, the trajectory remains untouched. The inertia is too large. You breathe in and recognize that the star above you, the same sun that pulls at every planet and bends every comet, does not shift this visitor. Atlas answers only to gravity, and gravity alone tells you how heavy it must be. The comparison with earlier visitors strengthens the picture. Oumuamua, long and thin, was light enough that its orbit could be nudged. Borisov, icy and fragile, carried less than a fraction of this mass. Atlas towers above them both, a record among interstellar bodies. You look back at those precedents and realize the pattern. Each arrival surprises, each breaks expectations, but Atlas does so with sheer bulk. The mass also reshapes how you classify it. With this kind of weight, the line between comet and embryo blurs. Comets are not supposed to be this heavy. Embryos are. Atlas moves closer to the category of planetary building block not because of speculation, but because the numbers force it there. Tens of billions of tons are not the remains of a crumb, they are the remains of a core. This weight demands the next question. If the mass is so vast, then the nucleus must reflect it. How wide, How solid, how large is the body that carries such inertia? The answer comes by measuring the size directly, and those numbers point to kilometers, the scale of mountains, not rubble. Size in the sky is never measured by sight alone. It emerges from shadows, brightness, and the way light scatters across a body hidden in distance. The estimates of Atlas place its nucleus among the largest ever associated with an interstellar visitor. Observations by Hubble in late July 2025 gave an upper boundary of roughly 5 to 6 kilometers across. That is not the scale of dust or rubble, it is the scale of a mountain drifting between stars. For comparison, the nucleus of Halley's comet is about 11 kilometers long. Borisov, the second interstellar visitor, measured closer to 1 kilometer. Oumuamua was at most 200 meters. Atlas stands between the giants of our system and the crumbs of earlier wanderers, a body whose size matches the numbers demanded by its mass. You lift your head to the night sky and the realization takes shape. What you're looking at is not a fragment, but a bulk. A traveller with a face measured in kilometers, carrying weight enough to survive eons of exile. The coma that surrounds it hides the details, but the math beneath the glow is clear. To shine this brightly, to hold steady against gas release, the nucleus must be immense. The surface of such a body cannot be guessed easily. Telescopes cannot resolve features at this distance. What you see is blur, and behind that blur could be ice hardened by ages, crust darkened by radiation, or even layers of rock forged in collisions. You follow the thought through the data, and the image becomes sharper in your mind. Atlas is not loose gravel. It is consolidated matter, pressed together until sunlight cannot move it. A nucleus 5 to 6 kilometers wide carries consequences. First, survival. Smaller comets often split or dissolve after a single close pass to the Sun. A body of this size shrugs off such risks. Even as it releases gas, the core remains intact. Second, visibility. The coma around a nucleus of this scale can expand and glow for months, making it easier for telescopes to follow. That is why images from Gemini South showed a clear tail in August 2025. The nucleus had the scale to sustain activity over time. You breathe in the night air and recognize how rare this is. Only 3 interstellar bodies have ever been seen, and this is the largest. Oumuamua slipped past almost unnoticed until it was gone. Borisov left quickly, a faint cometary visitor. Atlas towers over both, not in distance but in presence. It holds in its bulk the memory of a system we cannot see, and the dimensions tell you it is closer to a world's embryo than to a shard. This is why scientists struggle to classify it. A nucleus this large, carrying this much mass, stands at the border between comet and embryo. Numbers alone do not decide categories, but they push you toward a new language. To call Atlas a comet is to risk missing its scale. To call it an embryo is to risk saying too much. Yet the measurements remain: 5 to 6 kilometers, a body large enough to anchor its orbit against all perturbations. The question becomes comparison. What does it mean to see such a body after Oumuamua and Borisov? Each visitor has reshaped expectations, each one stranger than the last. Atlas forces the scale wider. To understand what it represents, the next step is to place it beside its predecessors. Comparisons reveal patterns that single objects cannot show, and the 3 interstellar visitors now form a sequence of strangeness that stretches our definitions further each time. Oumuamua, detected in October 2017, was the first. Small, elongated, less than 200 meters in size, it passed quickly and left confusion in its wake. Its light curve suggested a shape unlike anything seen before. tumbling and reflecting sunlight in odd rhythms. More disturbing was its acceleration. The body sped up slightly as it left the solar system, a change too large to ignore yet lacking any sign of a coma or tail. No gas jets were visible. Some explained it as unusual outgassing. Others, like Avi Loeb, argued it could be artificial, a thin light sail pushed by radiation pressure. Oumuamua departed before consensus could form, leaving behind a question rather than an answer. 2 years later came 2I/Borisov, discovered in August 2019 by amateur astronomer Gennady Borisov. Unlike Oumuamua, it looked familiar. A comet with a visible tail, active outgassing, chemistry similar to comets in our own system. Yet even Borisov carried differences. Its high dust-to-gas ratio, its unusual levels of CO and CN, marked it as foreign. Still, compared to Oumuamua, it was closer to what textbooks describe. It reassured observers that interstellar visitors could resemble known categories. Atlas changes that balance again. With a nucleus up to 6 kilometers wide and a mass in the tens of billions of tons, it is larger by far than either predecessor. Its orbit shows no unexplained acceleration like Oumuamua's, but also no subtle perturbations like Borisov's. The path is clean, gravity alone in command. At the same time, its coma glows green with chemistry that resists familiar explanations. You stand beneath the sky and feel the weight of this comparison. 3 visitors, 3 different faces, none of them truly ordinary. The sequence tells a story of increasing diversity. First, a sliver that accelerated without explanation. Then a comet that looked familiar but carried alien chemistry. Now a giant embryo-like mass, both cometary and not. Each step breaks expectations. Oumuamua was too small, Borisov too dusty, Atlas too heavy. Together they show that interstellar bodies cannot be contained by the neat labels of comets and asteroids alone. They carry the imprint of systems we have never seen. You tilt your head back and recognize how young this field is. 3 bodies in less than a decade define all of our knowledge of interstellar visitors. That is no sample size at all, yet already the differences are extreme. If the first 3 are this diverse, what will the next dozen look like? The question lingers heavier than the glow of any coma. The comparison also reveals why Atlas matters. Its size makes it more stable than Oumuamua, its activity stranger than Borisov. It sits between categories, and that tension fuels every debate. If Oumuamua tempted speculation with its acceleration, and Borisov reassured with comet-like behaviour, Atlas unsettles with its sheer scale. You breathe in the night air and accept that this one does not fit into a story of reassurance. It is a reminder that interstellar space holds bodies shaped by rules we do not share. Placed side by side, the 3 visitors mark a progression of strangeness. First a shard, then a comet, now a giant. Each tells us that what drifts between stars is not uniform. Each forces us to reconsider what survives ejection, what travels for millions of years, what endures enough to reach us. The future holds more, and each will widen the scale further. Atlas is not the end of the sequence. It is the point where the comparisons must begin. To compare bodies is one thing, but to open their spectra is to read their inner breath, and Atlas speaks in lines of light that do not match what we know. Spectroscopy has been the most powerful tool for understanding what Atlas is made of. When starlight or sunlight reflects through the gases that surround a comet, each molecule leaves a signature. Astronomers spread the light into its spectrum and find fingerprints. Water vapor reveals itself in certain lines, carbon dioxide in others, cyanide radicals in yet another set. With ordinary comets, The patterns are familiar. They breathe mostly water, with smaller traces of CO2, CN and other volatiles. Atlas does not break that rule completely. Its coma contains water, carbon dioxide and cyanide, the usual cast of molecules seen around icy bodies. The signatures were clear in the data. OH bands show in water, CO2 absorption lines, CN emissions. Nothing about their presence alone shocked observers. What shocked them was their proportion. Already the ratios hinted at imbalance, but the first fact was simple. Atlas is breathing alien air, and the chemical voices are recognisable but uneasy in tone. You follow the reports and the sense is direct. In the spectrum, water was faint, carbon dioxide stronger, cyanide faint but distinct. These results confirmed Atlas as active, not inert stone. You stand under the sky and know. The glow above you is not just sunlight bouncing off dust, it is gas being released, molecules escaping after millions of years locked in ice. Every time the sun warms its surface, another trace of its birthplace emerges. Telescopes at different wavelengths confirmed the story. Near-infrared observations with instruments like Webb's NIR-SPHEREc revealed CO2 in stronger amounts than expected. Ground-based optical telescopes confirmed CN in the coma. Ultraviolet traces gave evidence for water breakdown. All the usual players were present, but out of balance. The lines were shifted not in place but in weight, and that shift was the first sign that Atlas was not breathing in the same way as comets of our system. The presence of cyanide especially caught attention. CN radicals are common in cometary comae, formed when sunlight breaks apart more complex molecules. In Atlas they appeared faint but persistent, another sign that its chemistry was alive under the sun. Cyanide, a molecule that humans know as poison, here becomes just another breath of an interstellar embryo. You tilt your head back and accept how strange it is that something drifting from another star exhales, compounds once feared as deadly. The spectra confirmed the activity, but also set the stage for the deeper puzzle. Water was there, CO2 was there, CN was there, yet the proportions were wrong. What should have been a balance tilted heavily in one direction. That imbalance leads into the next question, the next step in the chemical mystery of Atlas. Why does carbon dioxide dominate so completely over water? Ratios tell more than presence, and in Atlas the balance of breath is reversed, a fingerprint of origins that do not match the nurseries we know. For most comets studied within our solar system, water dominates. Sublimation of H2O is the driver of cometary activity, the source of tails, the gas that shapes their orbits. Carbon dioxide plays a role, but usually as a trace, perhaps a tenth or less of the water content. Atlas overturns this expectation. Observations with near-infrared spectroscopy show CO2 outnumbering water by nearly 8-1. Such an inversion is rare, even among the diverse comets catalogued so far. The meaning of this imbalance is profound. It points to conditions of birth very different from those of comets in our system. If water ice was scarce where Atlas formed, then it must have condensed in a region closer to its star, or around a star hotter than the Sun, where high radiation stripped lighter molecules away. Alternatively, its protoplanetary disk may have carried an unusual chemical makeup, richer in carbon dioxide and poorer in water. You read the numbers and understand that Atlas is not only from another system, it is from a system with rules we cannot easily imagine. You stand under the night sky and feel the contrast. Earth's oceans, Earth's clouds, Earth's weather, all rely on abundant water. Atlas exhales with a breath almost empty of it. Instead, it gives back CO2, the gas that on Earth signals fire, industry, climate change. To see that ratio reversed is to look into a mirror where your own planet feels alien. The imbalance also explains part of the mystery of its mass. A nucleus rich in carbon dioxide would sublimate differently, releasing gas more efficiently at greater distances from the star. That may be why the coma glowed so early, even before close approach to the Sun. But the volume of water released remained low, so the usual cometary signs of strong jets never appeared. The chemical fingerprint is not only strange, it changes the way the body behaves under sunlight. This ratio affects colour as well. With less water vapour breaking into OH radicals, the balance of spectral lines shifts. With more CO2, the green glow recorded in September must have other explanations. The chemistry of Atlas is not broken, but bent, shaped by conditions no longer present in the solar system. You tilt your head upward and accept the chill in the thought. What you are seeing is the exhalation of a nursery long gone, preserved in numbers that do not belong to here. Comparisons highlight the peculiarity. Borisov carried water in proportions closer to our comets, though with higher levels of CO and CN. Oumuamua showed no coma at all. Atlas, by contrast, insists on being active but with a balance reversed. You breathe in the cool night air and the realization feels heavier. The chemistry above you is not familiar, and yet it is real. This is why scientists hesitate to file Atlas neatly under cometary categories. Numbers are not opinions. An 8:1 ratio of CO2 to H2O is not an illusion. It is a statement of origin. The ratios carry memory, the same way rocks on Earth preserve traces of their volcanic past. Atlas carries the memory of a different disk, a different star, a different time. Such imbalance sets the stage for the next mystery. If water is scarce, CO2 abundant and CN faint, then what explains the green glow captured by telescopes? The spectrum lacks enough diatomic carbon to account for it. The colour remains unexplained, a visible sign of chemistry that refuses the models. Colour is not decoration in space, it is signal, and Atlas shines with the shade that refuses the expected cause. In September 2025, during a lunar eclipse that dimmed the sky, enough for faint objects to be seen clearly, telescopes recorded Atlas glowing with a distinct green halo. This was not subtle. The coma around the nucleus radiated a colour that observers immediately associated with diatomic carbon, the C2 molecule, which has been responsible for the green hue of countless comets. Yet when spectrographs examined the light, the expected signature of C2 was missing or too weak to justify the brightness. The result was a contradiction, a glow without a source. You lift your eyes and accept the paradox directly. The light is there, the chemistry is not. Normally, when comets approach the Sun, volatile compounds break down under ultraviolet radiation. Diatomic carbon forms and fluoresces, producing a green coma that fades as the gas disperses. With Atlas, this mechanism fails. Something else must be driving the colour, but the data refuses to settle. Astronomers tested alternatives. Some suggested that CO2 dominance in the coma may trigger reactions that mimic C2 emissions under certain wavelengths. Others pointed to exotic compounds, carbon chains longer or shorter than usual, that could masquerade in the spectrum. Another possibility is that the nucleus contains reservoirs of organics never seen in our comets, releasing gases that overlap with the wavelengths associated with green. Whatever the explanation, Atlas does not follow the script of ordinary cometary chemistry. You breathe in the night air and the thought presses closer. This glow is not an illusion of instruments. It has been confirmed from multiple observatories. from ground-based telescopes to space-based platforms. The images show the halo consistent across nights, bright enough to notice, steady enough to resist dismissal. For centuries, green comets were linked to omens, their colour interpreted as poison in the air. Today the link is chemical, but with Atlas the chemistry is incomplete. A body from another system exhales in a way our models cannot match. The absence of sufficient C2 lines makes Atlas a case study in anomaly. If the coma is glowing green without the molecule that normally causes it, then either our understanding of cometary fluorescence is incomplete, or Atlas carries compounds never catalogued before. Both answers point in the same direction. Something about this visitor comes from a different set of conditions, not replicated in our solar system. The human response is immediate. You tilt your head back and feel the unease of watching colour stripped of cause. The eye sees, the mind cannot explain. In that gap, fascination grows. Scientists call it anomaly. You call it mystery. The mystery deepens because the glow persists. Weeks after first detection, the coma still radiates faint green. No sudden changes, no easy fade. It is not a transient flare. The source is steady, whatever it may be. That steadiness makes the question heavier. Something inside Atlas is producing or sustaining emissions that resist simple categorization. So the coma shines in green, the molecule is missing, and the models fail. What follows is the central puzzle. What really makes Atlas glow? Unanswered colour becomes more than appearance. It becomes a clue, a signal that the chemistry of Atlas is not the chemistry of here. When telescopes captured the glow of Atlas, the expectation was simple. Green means C2. Yet with spectral lines too weak to support the brightness, the question sharpened. If not diatomic carbon, then what? Laboratory studies of cometary materials show that other carbon-bearing compounds can fluoresce, but rarely with the same clarity or strength. Polycyclic aromatic hydrocarbons, complex chains of carbon and hydrogen, can release green emissions under ultraviolet radiation. Sulfur compounds can mimic faint traces as well, but the balance of wavelengths recorded in Atlas does not match any known template exactly. You stand beneath the night and feel the weight of that gap. The glow is undeniable, the explanation incomplete. It is as if a language is being spoken with familiar sounds but unfamiliar grammar. The coma breathes light in ways our catalogues do not contain. Some astronomers suggest that the dominance of CO2 in the coma changes the chemistry at a fundamental level. When carbon dioxide is broken apart by sunlight, it can lead to reactive fragments that drive chains of emission rarely seen in our comets. If Atlas formed in a disk richer in CO2 than H2O, then the molecules released now would follow chemical pathways that are alien to us. The green light could be the visible face of that difference. Not a single molecule, but an interplay of many, producing a spectrum that resembles C2 without being it. Others point to the possibility of unknown compounds altogether. Interstellar space is filled with complex molecules, many detected only in radio bands from distant clouds. If some of those were locked into the ices of Atlas, then sunlight may now be revealing their signatures. In this view, the glow is not a puzzle to be solved by tweaking models of C2, but evidence that the body carries chemistry we have never measured before. You breathe out slowly and accept that possibility. Above you shines a laboratory sample, delivered from another star, and it refuses to match the patterns you know. The persistence of the colour strengthens the case. Night after night, the coma continues to radiate green. If it were a transient flare, the question would fade. Instead, the glow remains steady, a constant reminder that the explanation is missing. Even skeptics admit that this is unusual. The data does not allow a quick dismissal. For the public, the green light becomes a symbol. A comet glowing in emerald tones is an image with deep roots in folklore. It recalls centuries of fear when such colours are taken as poison. Today the fear is replaced by wonder, but the fascination is the same. You tilt your head upward, and the glow feels less like scattered sunlight and more like a message, though reason insists it is chemistry, not intention. The scientific weight of the puzzle is different. For researchers, the green glow is a sign that planetary formation can produce bodies with chemistry beyond local norms. Atlas may not only be a comet from another system, it may be a chemical fossil, carrying reactions from conditions our Sun never provided. Each photon it emits is a trace of a laboratory we cannot visit, except through this one refugee. So the question stands, what really makes Atlas glow? The answers remain open. Perhaps hidden organics, perhaps exotic carbon chains, perhaps chemical pathways unlocked only in CO2-rich ices, or perhaps something not yet imagined. The glow continues, steady and unexplained, and until its cause is found, the colour will remain a reminder that not every mystery of Atlas can be solved by the models we bring to it. Light was only part of the puzzle. Soon photographs revealed shape, a thin extension trailing from Atlas that marked its transformation from a blur into a cometary figure. In late August 2025, the Gemini South Telescope in Chile released images that changed how Atlas was seen. Until then, it has been a glow, a coma with strange chemistry and unexplained colour. The photographs showed something new, a tail, thin, faint, stretched into the dark. The structure confirmed that material was leaving the body. A comet without a tail is already a curiosity. A comet with one is undeniable. The extension behind Atlas meant gas and dust were escaping, carried by sunlight into space. Hubble followed with its own observations. High-resolution images taken in July and August revealed not only the halo, but a subtle elongation, the first hints of a developing tail. When Gemini's wider field confirmed it weeks later, the image was clearer. Atlas was active. No longer just a point of mystery in spectral charts, it displayed the most recognizable feature of a comet. You look at those photographs and the impression fixes itself. The green coma, the faint trail behind, together they tell you that Atlas is alive under solar radiation. Ices are sublimating, particles are being released, and the object responds to heat as comets do. Yet even here, the details resist simplicity. The tail was thinner than expected, more fragile in structure, less dramatic than the plumes of Halley or Borisov. For such a massive body, the outflow looked restrained, as if weight itself suppressed the show. The appearance of the tail was late compared to ordinary comets. Many begin to sprout plumes at greater distances, their activity visible months earlier. Atlas stayed quiet longer, then showed its trail only as it drew nearer. This delayed reaction added to its strangeness. You stand under the sky and let the thought sink in. The visitor responds, but in its own rhythm, not in the rhythm our models predict. The first photographs also raised questions about what lies ahead. If the tail is already visible at this distance, how will it evolve closer to the Sun? Will it remain faint or grow into something dramatic? The comparison with ordinary comets suggested growth, but Atlas had already shown that it rarely follows rules. The pictures from Gemini and Hubble did more than confirm activity. They sharpened the anticipation of what perigee would bring. Activity in comets usually begins early, flaring as soon as sunlight reaches volatile ices, yet Atlas waited longer, holding its silence until distance shrank. The late awakening of Atlas was one of its defining surprises. In comets of our system, activity often starts beyond the orbit of Jupiter, sometimes even earlier. Water ice is not the only volatile. Carbon monoxide and carbon dioxide can drive outgassing at great distances. Plumes appear while the body is still far from the sun, building a coma that expands for months. By the time most comets cross the inner system, their tails are already established, long and dramatic. Atlas did not follow this pattern. For weeks after its discovery, observers reported only a blurred coma with unusual chemistry. No tail, no clear activity beyond faint gas. Only in late summer did the first structures begin to emerge. This delay puzzled astronomers. With its mass and scale, Atlas should have shown signs sooner. The chemistry suggested carbon dioxide dominance, a volatile capable of driving activity far from the sun. Yet for reasons still debated, the body stayed quiet longer than expected. Some proposed that a hardened crust insulated the interior, keeping gases trapped until the heat penetrated deeper. Others suggested that the orientation of the nucleus hid active areas from view, with sublimation starting only as sunlight reached the right face. Whatever the mechanism, the result was the same. Atlas resisted the early flare that defines typical comets. You stand beneath the night sky and think about the silence of that waiting. An object travelling for millions of years across interstellar space, carrying volatile ices in its depths, arrives here and still refuses to speak until pressed closer. The patience of such a body feels alien compared to the rest of cometary behaviour. It gives up its chemistry slowly, almost reluctantly, as though conserving itself for the long journey still ahead. The delayed activity also explains why its tail looked thin when it first appeared. Instead of months of build-up, Atlas began releasing dust and gas only recently. The structures had less time to expand, less distance to spread before being photographed. What telescopes caught was the first stage of a process usually far more advanced by the same distance. Late blooming left Atlas looking restrained, a giant that moved with the rhythm of its own choosing. This behaviour has precedent, but rarely at such scale. Some comets in the Oort cloud show delayed activation, but they are smaller, less massive, easier to explain. For a body this large, with chemistry tilted so heavily towards CO2, the late start remains a contradiction. You tilt your head and let the thought rest. The visitor follows rules not entirely ours, answering heat with the schedule written in another nursery. The consequences of this delay matter. It means predictions of what Atlas will look like near perigee must be cautious. If it activates late, it may also flare late, surprising observers with sudden intensity. Or it may remain subdued, shedding only faint streams despite the heat. Either way, its rhythm is its own. To understand how unusual that rhythm is, the only path is comparison, setting Atlas against the long record of comets that have passed through the inner solar system before it. Comets of the solar system have been observed for centuries. Halley's Comet has been tracked for more than 2,000 years, returning every 76 years with a predictable blaze of light. Its nucleus is about 11 kilometers across, its tail stretching millions of kilometers when close to the sun. Brightness rises early, long before perihelion, and activity continues long after. Other comets, Hyakutake in 1996, Hale-Bopp in 1997, Neowise in 2020, all showed similar patterns. Tails grew long, comae expanded wide, and activity started early, driven by ices that evaporate at great distances. Atlas, by contrast, broke that expectation. The delay in activity meant its tail was still faint even at distances where most comets already blaze. The scale of its nucleus should have produced an early and dramatic show, but instead observers saw a restrained release. You stand under the night sky and recall images of Hale-Bopp filling the horizon in 1997. Then you look at the slim, hesitant tail of Atlas in 2025 and feel the dissonance. Both are comets in name, yet their behavior is not the same. Brightness is another measure. Ordinary comets brighten rapidly as they approach the Sun, often exceeding predictions. Atlas did brighten, but the numbers did not follow the steep curve typical of water-rich comets. Its dominance of CO2 meant different thermal behavior. Instead of the surge driven by water vapor, the glow remained steadier, tied to carbon dioxide's lower sublimation temperature. The result was a pattern flatter than expected, a visitor that glowed green but resisted the full blaze of spectacle. Dust release also differs. Hale-Bopp and Hyakutake filled their tails with dust particles, creating wide fans visible to the naked eye. Atlas shed less, its dust-to-gas ratio lower, its tail thinner. The contrast suggests that either the nucleus is less dusty, or its surface locked dust beneath a hardened crust. Whatever the reason, the impression remained. Atlas is not generous in display. It keeps more of itself, revealing less to telescopes than comets of comparable size. Even orbital effects reveal difference. Halley's orbit shifts predictably with each return, its path altered slightly by jets. Smaller comets show even larger perturbations. Atlas remains untouched. You tilt your head back and accept what the charts confirm. This interstellar visitor carries too much mass to be steered by outgassing. The Sun shapes its orbit only through gravity. In this way, Atlas behaves less like a comet and more like a small planet passing through. The comparison teaches caution. To call Atlas a comet is correct by activity. It has a coma, it has a tail, it sublimates under sunlight. Yet the details, timing, brightness curve, dust ratio, orbital stability, show a body that does not fit comfortably within the pattern. You breathe slowly under the stars and feel the truth. It shares features with comets, but does not belong to them fully. It sits between categories, its own kind of visitor. If Atlas is not like ordinary comets now, what will happen when it draws closer? When the heat of the Sun presses harder? Will the late start turn into a late blaze, or will the same restraint continue? The next stage of its journey will test those questions. Approach to the Sun is the great trial of every comet, and Atlas is now moving toward the point where distance can no longer shield it from heat. In late October 2025, Atlas will reach perihelion, its closest approach to the Sun, at about 1.4 astronomical units, just beyond Earth's orbit. For comets, this stage is decisive. The increase in solar energy is steep, each unit of distance inward multiplying the heat received. Bodies that seemed calm can erupt with sudden flares, jets and outbursts. Others, weakened by earlier passes, break apart before completing their journey. Atlas, massive and interstellar, faces this trial for the first and only time within our system. Predictions remain cautious. Its delayed activity suggests a body that does not follow the familiar timeline. Some astronomers propose that its crust may fracture as the heat intensifies, exposing fresh layers of volatile material. If that happens, the tail could grow quickly, transforming the faint streak into a luminous banner stretching across millions of kilometers. You look at the sky now and imagine how that would change. From a thin thread into a spectacle bright enough to rival the brightest comets in history. Others warn of restraint. With such mass, Atlas may vent gases without producing dramatic displays. The same inertia that kept its orbit steady against outgassing may also suppress visible transformation. In that case, perihelion could pass with only modest brightening. A green coma glowing but not flaring, a traveller too heavy to perform. You tilt your head upward and accept that uncertainty. Both futures remain possible, and neither can be ruled out. There is also the question of survival. Smaller comets often split near perihelion, their weak structures collapsing under the stress of heat and tidal forces. Atlas is different. Its size, 5 to 6 kilometers across, suggests resilience. Few expect it to fragment completely. Still, the chemistry complicates the prediction. A CO2-rich body may react violently when fresh layers are exposed, creating sudden bursts that crack its surface. If that occurs, new plumes may form abruptly, changing its appearance within days. You breathe the cool night air and recognize how little precedent exists. Only 3 interstellar bodies have been studied, and none as massive as this. There is no catalogue to consult, no model to lean on with confidence. Atlas carries the unknown into perihelion, and its behaviour will set the standard for what massive interstellar comets can do under a star's close gaze. The anticipation is global. Telescopes across the Earth, from Hawaii to Chile, from Spain to South Africa, prepare to follow every moment. Space-based observatories like Webb and Parker Solar Probe will have unique vantage points, measuring spectra, plasma interactions, and tail dynamics. The next months will be filled with data. You stand under the stars tonight and realize you are watching the calm before the heat. As the days shorten and October nears, the predictions remain open. Will Atlas flare into brilliance or remain restrained? Will it show resilience or surprise with sudden cracks? The perihelion will answer, but until then the object remains suspended in uncertainty. Uncertainty grew sharper when polarimetric instruments turned to Atlas and revealed a signal almost never seen, an extreme negative polarization that defied expectations. Polarization is the fingerprint of light after it scatters off dust grains. By measuring the angle and intensity of polarization, astronomers can learn the size, shape, and texture of particles in a comet's coma. Most comets show a typical curve. Polarization grows with phase angle, the geometry between sun, comet, and observer. Atlas, however, broke this rule. Measurements taken in August and September 2025 by instruments such as FORCE 2 on the VLT, ALFOSC on the Nordic Optical Telescope, and FORERO 2 in Bulgaria showed something extraordinary. Extreme negative polarization at phase angles where comets usually show positive values. This means that the dust surrounding Atlas is not scattering light in the ordinary way. Instead of enhancing polarization as angles widen, the coma reversed the trend, producing values far below expectation. Negative polarization is not unknown. Many comets display it at very small phase angles, but the degree recorded for Atlas was exceptional. The numbers dropped lower than almost any previously measured comet. You follow the data and feel how alien this response is. Ordinary cometary dust, mixtures of silicates and carbonaceous grains, cannot easily explain such depth of negative polarization. It suggests particles with unusual structure, perhaps compact aggregates shaped differently, or surfaces altered by long exposure to interstellar radiation. The light tells you directly, this coma is built from dust, not typical of our solar system. The implication unsettles models. If dust grains are compacted differently, they may reflect sunlight in ways that mimic brightness without mass. This could explain why Atlas shines so strongly while appearing too thin in dust for the light it produces. You stand beneath the night sky and let the fact settle. The glow above you is not only chemistry, but optics, particles scattering light in patterns unseen before. Extreme negative polarization becomes a clue as sharp as any spectrum. It points to a composition or structure foreign to our catalogues. It says that the dust of Atlas may have grown under pressures or conditions absent in our protoplanetary disk. For a body that has travelled across interstellar space, this is not impossible. It is in fact expected, but the degree still shocks. This leads to the next question. If the coma behaves optically in ways so unusual, how much of its brightness is true reflection, and how much could be something else? Brightness then becomes the next puzzle, because light does not only scatter, it can also be made, and Atlas shines with an intensity that forces the question of source. Comets are supposed to shine by reflection. Sunlight strikes their dust, photons scatter, and to the human eye or the telescope the coma glows. The nucleus itself is dark, albedo low, surfaces blackened by carbon compounds. The rule is simple. Comets do not emit their own light. They reflect. Yet Atlas has not stayed inside that rule. From the moment its coma was measured in August and September 2025, its brightness appeared stronger than the mass of visible dust could explain. Some astronomers suggest that the unusual polarization already offers part of the answer. The dust is reflecting in ways not seen before, amplifying the glow. Others, however, see a gap too wide. If dust alone is responsible, then it must be extraordinarily efficient, far beyond what current models allow. The numbers resist closure. You read those reports and feel the weight of anomaly. Too much light for too little matter. It was Avi Loeb who made the most radical claim. He proposed that Atlas might not be reflecting alone, that it could be emitting, generating light from within. To suggest intrinsic luminosity is to break the cometary definition altogether. Yet the data that troubles reflection opens the door to such ideas. A nucleus estimated at 5 to 6 kilometers across, with mass in the tens of billions of tons, could in theory hold radioactive decay or other processes capable of releasing energy. You tilt your head back and the thought presses close. If a body from another star glows by itself, what does that mean about its nature? For now, mainstream science remains cautious. No clear evidence supports intrinsic emission. The glow lacks the spectral fingerprints of thermal radiation. No narrow lines betray technological light. The coma still looks like gas-scattering sunlight, yet the mismatch between dust content and brightness keeps suspicion alive. You stand under the stars and admit what scientists themselves confess. The data leaves room for more than one answer. The debate matters because it shapes classification. If Atlas is only reflecting sunlight, then it remains a comet. Strange, heavy, interstellar, but still a comet. If it emits, then it crosses into another category, one without precedent. A luminous embryo would not be a fragment but an active body, an object capable of more than passive reflection. That possibility alone is enough to hold attention. The strength of the glow may also connect back to its chemistry. CO2-dominated sublimation could release fragments that scatter light differently, perhaps mimicking emission. If so, the explanation is still natural, just unfamiliar. But if not, then Atlas remains an open question, its brightness hovering between dust and something more. So brightness becomes the next doorway. Reflection cannot fully explain it. Emission is not proven. Atlas glows, and that glow refuses to be settled. The next step is to examine the images themselves, the photographs taken by Hubble. which revealed shapes and extensions that only deepened the puzzle. Images from Hubble rarely disappoint, and when its mirrors turned toward Atlas in July and August 2025, the blur sharpened into detail that made the mystery larger, not smaller. The Hubble Space Telescope first observed Atlas on July 21st, 2025. At that time the comet was still faint, yet the resolution of Hubble revealed a coma with a distinct teardrop shape. The nucleus itself remained unresolved, too small and distant for even Hubble's sharp eye, but the surrounding halo stretched asymmetrically, suggesting directional outflow. That asymmetry marked Atlas as active even before ground-based telescopes confirmed the presence of a tail. Later in August, further Hubble images showed a clearer extension trailing the nucleus, a subtle tail only beginning to form. The brightness profile was unusual, sharper near the nucleus, fading more slowly than typical comets. This indicated that particles were either larger or reflecting light differently, echoing the findings from polarization studies. The coma did not scatter light as expected, but concentrated it in patterns that made Atlas appear brighter for its dust content. You study those images and feel the strangeness directly. Where you expect a diffuse glow, you see definition. Where a comet should blur evenly, Atlas sharpens into asymmetry. The green tint captured in some processed frames added to the effect, a luminous body that looks alive, radiating not just brightness but character. The shape also resisted simple modelling. Normally, cometary comae spread in radial symmetry. Atlas displayed directional features, faint jets, possible plumes, arcs of dust curving from one side. Yet the orbit showed no reaction to these releases. Another paradox. Gas was leaving, but the body did not move. You tilt your head and let the contradiction sink in. Activity without consequence. Outflow without drift. Hubble's instruments confirm the chemistry too. Spectra taken alongside images revealed the same imbalance of CO2 over water and the faint presence of CN. The visual and the chemical aligned. Atlas looked different, and it breathed differently. It was not an illusion of instruments. Every layer of data repeated the same message. This visitor was outside ordinary categories. For the public, the images became symbols. NASA released processed photographs showing the faint tail and coma glowing against the starry background. Media carried them worldwide. To casual eyes, it was a comet, yet the details told another story. You stand beneath the night and realize what those photographs represent: the most detailed look humanity has ever had at a massive interstellar body. And even at this scale, it refuses to behave like a comet should. The paradox of Hubble's view remained central. The images proved activity but not fragility. They showed jets but no orbital shift. They revealed a coma but with brightness unmatched by dust content. They deepened the glow's mystery and prepared the ground for the final problem. How can all these clues fit into a single explanation? Puzzles in science rarely come as single riddles. They arrive layered, each answer creating another question, and Atlas has become one of the most layered puzzles in modern astronomy. Atlas now sits at the intersection of conflicting data. Polarization points to dust unlike any measured before, compacted or altered by interstellar travel. Brightness exceeds expectations for the amount of material visible, raising the possibility of scattering efficiency never modelled or even intrinsic emission. Hubble images show jets, asymmetries, arcs of dust, yet orbital charts confirm stability too perfect to betray them. Chemistry adds its own contradictions. Water scarce, CO2 dominant, green light without enough C2. Each line of evidence feels consistent in isolation, but together they clash. You stand under the sky and let that contradiction press on you. A body cannot both vent gas and remain immovable, yet Atlas does. A coma cannot glow green without molecules to produce it, yet Atlas glows. Dust should scatter light in predictable ways, yet Atlas bends the rules. Each observation is real, but they do not form a single picture. Scientists call this a degeneracy of models. Too many parameters, not enough certainty. Adjust the grain size and brightness fits, but polarization fails. Change the chemistry, and the green light is explained, but the ratios collapse. Propose intrinsic emission, and the physics stretches too far. Every solution leaves another gap. The feeling of incompleteness is familiar in astronomy. Oumuamua left with acceleration unexplained. Borisov departed with chemistry unusual but still acceptable. Atlas combines both, a hybrid anomaly. You breathe in the night air and admit what researchers have written in their notes. The object remains unresolved, a system of contradictions waiting for more data. The puzzle is not only technical, it reshapes definitions. If Atlas is classified as a comet, then comets must include bodies this massive, this strange. If called a planetary embryo, then embryos must include activity more like comets than planets. If called artificial, then evidence falls short. Categories bend under the weight of anomaly. This is why Atlas is called a scientific challenge. It is not one question, but many, about dust, light, chemistry, activity, and classification. Each telescope adds detail, but detail does not yet converge. You tilt your head upward and know the truth. Atlas is a reminder that the universe is under no obligation to fit our labels. The next months will bring more data. Perihelion, global observation campaigns, spectra from Webb, images from Parker Solar Probe. Each will add another layer. The puzzle may resolve, or it may deepen. For now, Atlas remains a body defined not by certainty, but by tension. That tension will sharpen as Atlas moves, for its path is already written across the solar system, carrying it past Mars and toward the Sun itself. In early October 2025, Atlas will brush past Mars, not in impact but in proximity. Its orbit brings it within 0.19 astronomical units of the red planet, about 29 million kilometers. That distance is vast by human standards, yet in astronomical terms it is close. Close enough that Mars-based missions and telescopes on and around the planet can capture the visitor. For comparison, Earth and Mars are often separated by hundreds of millions of kilometers. Atlas will glide past at less than 1/5 of that. You picture the geometry. Mars circling the Sun, its thin atmosphere glowing faint in the light of dawn, and above it this interstellar traveller cutting by, visible not as a threat but as a guest. Robotic eyes on the planet, from rovers, orbiters, and perhaps even improvised camera settings, will aim upward, trying to record a body from another star passing nearby. For the first time in history, a world beyond Earth may witness an interstellar comet at close range. This flyby also offers science. Dust streams shed by Atlas may interact with the Martian atmosphere. The faint tail may sweep particles into space near Mars's orbit. Instruments designed for other purposes could register anomalies in plasma, radiation, or micrometeorite impacts. Atlas does not collide, but its presence is felt. For planetary science, this is a rare experiment handed over by chance. Only weeks later, the real trial arrives, perihelion. On October 29th to 30th, 2025, Atlas will make its closest pass to the Sun, The distance, about 1.4 astronomical units, places it just beyond Earth's orbit. For ordinary comets, perihelion is a moment of transformation. Ice sublimates furiously, tails flare, nuclei fracture. Some survive to loop back, others disintegrate into dust. Atlas is different. Its hyperbolic trajectory means this is its only visit. The outcome matters because it defines what we will ever know of it. Predictions diverge. The mass and stability suggest resilience. A nucleus 5 to 6 kilometers across should endure the heat without breaking. Yet its chemistry, CO2 dominance, faint water, unexplained green glow, leaves open the chance of surprises. A crust fractured by sudden heating could release hidden pockets of gas, producing jets unseen before. The tail could swell into a vast structure, or it could remain muted, a giant that refuses spectacle. You tilt your head beneath the stars and accept the uncertainty. Both paths remain possible. The perihelion also tests classification. If Atlas responds with violent outbursts, it confirms comet-like behavior at its core. If it remains quiet, resisting even the closest heat, then the argument for planetary embryo grows stronger. Either outcome reshapes our sense of what interstellar bodies are. So the path past Mars and down to the Sun sets the stage. Atlas carries itself steadily, but heat will press harder, and telescopes across the Earth and in orbit will be watching. The traveller has passed one planet and is moving toward the star that will decide what face it shows us. After perihelion, the orbit bends away, carrying Atlas past Earth at a safe distance, while its deeper origin remains hidden in the darkness from which it came. The closest distance between Atlas and Earth will be about 1.8 astronomical units, more than 270 million kilometers. That is far beyond any danger. It will not sweep close enough to threaten our world or even to be seen clearly without telescopes. Yet in that distance lies significance. The orbit confirms that this is a true visitor, not a returning comet. Its trajectory is hyperbolic, open, a path that will never close into a loop. After October 2025, Atlas will continue outward, fading into space, leaving only data, images, and questions behind. For Earth-based observers, the geometry matters. At 1.8 astronomical units, the object will never become bright enough for naked eye spectacle. But telescopes will record its coma, its tail, and perhaps changes triggered by perihelion. Instruments sensitive to infrared and ultraviolet light will follow its chemistry as long as possible, mapping how the ratios of CO2, water, and CN evolve as it recedes. You stand under the night sky and accept the perspective. Even in passing, Atlas refuses intimacy. It is close by astronomical scales, yet remote enough to remind us that interstellar visitors rarely come within reach. The greater question stretches further back. If Atlas is not ours, then where was it born? Orbital analysis shows a hyperbolic eccentricity above 6, the highest yet recorded for such a body. That number alone tells you this object was ejected from another star system not captured here. The challenge is tracing the path in reverse. Millions of years of gravitational tugs erase precision. A single deflection by a passing star can alter the line beyond recovery. For Atlas, the uncertainties multiply. Its inbound direction points roughly toward the constellations of Pisces and Cetus, but no single star has yet been identified as its source. Some models suggest that Atlas may have originated in a young system with massive planets, ejected during chaotic early formation. Others propose it could have wandered from deeper interstellar space, part of the vast population of orphaned bodies stripped from their homes over billions of years. The galaxy is expected to hold more such wanderers than stars themselves. Atlas may simply be one of the rare few we have caught in the act of passing through. You breathe slowly and let the scale settle. The body above you may have crossed light years of empty dark before arriving here. It may have left its birthplace when Earth was still young, or even before Earth existed at all. Now it cuts across our sky, silent testimony to events in a system we will never see. The enigma of origin lingers. Without precise backward tracing, Atlas remains a refugee without a home address. Yet that fact itself is revealing. It shows how porous the galaxy is, how systems do not stay isolated but exchange fragments. Planets are built, broken, and thrown out. Some survive to orbit their stars, others, like Atlas, survive exile and continue across the void. So the journey through our solar system is brief. A pass near Mars, a trial at perihelion, a distant glide past Earth, then departure, back into the deep where origins dissolve. Atlas comes close enough to measure, yet far enough to keep its birthplace hidden. The visitor carries secrets beyond calculation, reminders that what passes overhead is not just foreign, but ancient. The journey of Atlas through our system is not finished, and the months ahead will decide how much of its nature we'll uncover before it slips away forever. Instruments are already aligned. The James Webb Space Telescope has turned its infrared eyes on the visitor, reading the fingerprints of molecules released from its surface. Webb's sensitivity to CO2, H2O, and organics allows it to measure composition with precision impossible from the ground. Data taken in August confirm the dominance of carbon dioxide, but more campaigns are scheduled around perihelion. These will track how chemistry shifts as heat rises, whether water increases, whether the strange green glow can be tied to new reactions. Webb will continue to follow until brightness fades below its limits, each spectrum a window into conditions that shaped a world we will never see directly. Another mission, SPHEREx, designed to map the sky in infrared light, will cross-check those results. Its wide field of view allows not only the study of Atlas, but also the search for other interstellar objects. SPHEREx may place Atlas into a larger context, comparing its chemistry with the background of interstellar dust. If Atlas carries compounds never seen in local comets, SPHEREx might reveal whether such anomalies are unique or part of a broader population. By the end of its campaign, we may know if Atlas is a solitary exception, or the first glimpse of a larger pattern. Closer to the Sun, the Parker Solar Probe will play its own role. As it loops around the star, Parker carries instruments that measure solar wind, dust, and plasma. During its passes in late 2025, it will cross regions near Atlas's projected path. Though not built to study comets, Parker has already captured images of comet tails interacting with solar wind. With Atlas, it could record changes in plasma density, the bending of magnetic fields, or even pick up particles stripped from its tail. You stand under the night sky and realize what that means. A spacecraft diving through the sun's fire may return traces of a body from another star. Perihelion itself is the climax. On October 29th to 30th, 2025, Atlas will come to within 1.4 astronomical units of the Sun. For most comets, this is the moment of greatest spectacle, when heat drives jets, tails flare, sometimes nuclei fracture. Atlas is different. Its hyperbolic orbit means this is its first and last pass. Whatever it does near perihelion will be the only close-up act humanity will ever see. If it remains restrained, its mystery will deepen. If it erupts, we may witness jets and fragments that reveal its interior. Telescopes across the Earth, from Hawaii to Chile, from the Canary Islands to South Africa, will follow every minute. Observatories in orbit, including Webb and Hubble, will capture spectra and images. Ground-based instruments will track brightness curves, dust release, and tail length. For weeks, the solar system's scientific focus will converge on one point of light. What might those new observations reveal? The chemistry could clarify. If water remains faint even at perihelion, then Atlas is truly alien, forged in a nursery where water was scarce. If water surges, hidden layers may lie beneath its crust. The green glow may find explanation in new compounds, revealed at higher temperatures, or it may persist unexplained, proof of pathways outside our models. Dust release could answer questions about mass. Large grains would confirm its density. Fine dust would shift the estimates. Even its tail's interaction with solar wind could redefine how we measure interstellar bodies. Each observation is a piece, and together they may build an image closer to truth, though perhaps still incomplete. You breathe in the cool night air and sense the scale of what is coming. This is not just another cometary campaign. It is a once-in-history convergence,